All right, now that we know about Hubble's law of the expansion of the universe, and we've established the Big Bang theory that the universe had a beginning and has been expanding from that on, let's remember what uh, Einstein had thought about the way of keeping the universe from collapsing. Einstein believed in an infinitely old, stable universe, and so he found that the cosmological constant in his theory of gravity, capital lambda, uh, had a repulsive effect. It would repel things that were very far apart from each other. And this would balance the universe out and keep it from collapsing. After Hubble found the universe was expanding, then there was, of course, no need to rely on a cosmological constant, and Einstein retracted this. But the math still allowed a cosmological constant. And over the century, people had been searching to see if there was a cosmological constant and always came up with it essentially equal to zero. Now, by the late 1990s, however, two teams of scientists, Saul Perlmutter in California leading one team, and then Bob Kirchner at Harvard, I believe, leading another, had been looking at distant supernovas. And this was a way of measuring how much the universe was slowing down as it expanded. Because again, if gravity is an attractive force, then as it expands, it will be slowing down over time. The question had always been whether the universe was slowing down a lot, in which case it might stop expanding completely and collapse back in on itself, forming a so-called big crunch, or slow down very, very little, in which case it would expand forever without limit, or maybe it would be just the right amount and it would slow down to a maximum size that it would never quite reach. It would asymptotically approach a maximum size, sort of a critically balanced universe. Now, all three of these presume that it's slowing down. And the amount that it's slowing down depends on how dense all the matter in the universe is packed in there. So how much matter divided by how much space is in the universe, the density. Now, if the density were very large, we would have what's called a closed universe. And this closed universe would collapse back in on itself after a certain amount of time. Since we're expanding now, then we obviously have not reached that contracting phase, but it could still be out there. If the density were much lower than that, it would expand forever. That would be called an open universe. And if it were just in between those two cases, with the density equal to some critical amount, this is called a critical density, then it would expand up to a limiting size but never quite reach that size. And that, to tell you the truth, was what many of us were hoping it would be. It was a much more pleasant kind of a fate for the universe rather than the big crunch in which everything is destroyed in a gigantic fireball, really a replay of the Big Bang backwards, or a drifting apart where everything gets cold and isolated by itself after billions, trillions of years and whatnot, and that's the end of it. So a very hot end or a very cold end, and still rather unpleasant ends. So that critical density case was what a lot of us wanted. But it's a matter of what nature really is rather than what we want. So both of these teams were looking to see if they could find out how much the universe's expansion was slowing down. Now, a way of doing this is to see what was the expansion rate in the distant past. You measure the expansion rate today, Hubble's constant, by looking at plotting the distances to galaxies and their redshifts. So velocity from redshift versus distance gets you this sloping line, which is Hubble's constant, Hubble's law. Now, if you go farther back in time by looking farther away, because the farther away you look, the farther back in time you see, then you could see if the slope, that is the expansion rate, Hubble's constant, was different. And we expect, of course, that the expansion rate would have been higher in the past and lower now. So you'd get the plot for Hubble's law would be steeper in the past and it would be shallower now. Well, what they found out was if you use supernovas, which you can see from very, very far away, you can measure their distances with one way, and you can measure their redshifts from the spectral lines. If you do this, you find out that in fact the universe was expanding more slowly some billions of years ago and faster now. So that Hubble law plot we did earlier starts to not quite flatten out, but the slope shallows as you go to farther and farther distances, that is, back farther in time. This means that the universe's expansion is speeding up. Now, this was really unexpected, and from my understanding, that this was there was concern as to how far they should stick their necks out on a pretty radical result then, without any other experiments yet to back it up. But they did, and they turned out to be right. And this discovery of the acceleration of the universe, powered by some undiscovered force, an unknown source of energy, which has now been called dark energy. Dark in this case means we don't know what it is. This won the Nobel Prize in 2011 for physics. Saul Perlmutter in California, and then the other half was won by Adam Rees and Bob Schmidt, I believe, Schmidt, both from Harvard and now working elsewhere. Adam Rees is at Space Telescope Science Institute. So this was recognized very quickly as a very exciting result. It was rather quickly confirmed by other experiments using different techniques, and the acceleration of the universe was established. This meant we weren't in fact slowing down at all. There was no deceleration. It was accelerating, which required a source of energy, and this is the so-called dark energy. Now, to tell you the truth, I'm not really good at explaining the differences between the, if any, between the idea of the cosmological constant, dark energy, other physical explanations for this. And that you'd have to go to some of the newer literature. But basically, Einstein was right without having known it in his lifetime. He died back in the 50s, long before this was found. So the cosmological constant, or some version like this, turns out to be correct. And this means that as we understand it now, the universe expanded very quickly in the early phase, it slowed down later, and now it's accelerating again, it's speeding up. And it looks like it will expand forever. Now, the shape, there's a geometry to the universe depending on how much mass is in it. If we did not have a cosmological constant, under the old idea, if the universe were ready to collapse, if it were going to collapse again, then it would have a curvature that's, let's imagine you've got a two-dimensional universe that can be curved by gravity through our three-dimensional space, an extra third dimension. Now, really we have a universe with 3 dimensions of space, which is effectively curved through an unseen 4th dimension. But we can't visualize that because we're 3-dimensional creatures. So let's imagine a 2-dimensional universe that gravity will bend through a 3rd dimension. Remember, Einstein's theory of gravity is that mass curves space, and that's what we experience as gravity. So a closed universe with a high density would have a so-called positive curvature, which we can represent by a sphere. It would close back around on itself. Now think of that two-dimensional universe as just the surface of this sphere. It's not the volume inside it. That doesn't exist in that universe. It's like little creatures living on an expanding balloon on the surface of the balloon. And they don't have a concept of up or down or inside or outside of the balloon. They're just on the skin. Now, in this kind of a closed universe, you could actually go all the way around it and back to where you started. A light beam shown in one direction would eventually come back and hit you in the back of the head. And in fact, if it were small enough, if the universe were small enough, you might actually be able to see the back of your head if you were able to see with a powerful telescope. You would appear to see yourself upside down and magnified at some distant point in space. So that would be the denser universe case, the closed universe. If the universe had that critical density, then it would have a flat geometry, where it would be just even on the large scales. Now, notice that I've drawn triangles here. If it were flat geometry, then it's not like normal plane geometry. A triangle has interior angles that add up to exactly 180 degrees. But on the surface of that sphere, with the positive curvature for the denser case, the interior angles of the triangle add up to more than 180 degrees. It looks puffed out and rounded from our point of view looking from the outside. Now, if it had um, a negative curvature is the third possibility if it were going to be an open universe, in which case it would have a curvature that's sort of saddle-shaped from our way of looking at it, and in which case a triangle drawn on that would have total angles adding up to less than 180 degrees. So without a cosmological constant, under our old cosmology, closed universes have positive curvature. Critically uh, dense universes have flat curvature, no curvature at all, Euclidean space, and open universes have negative curvature. But now that we understand that we have dark energy, there is a cosmological constant, now things get a little mixed up. It turns out that we have a very flat universe. So the geometry is flat, but at the same time, our universe appears to be open, in that it appears it will expand forever.